So, boys and girls, we continue to the second part of our discussion in today's tutorial. We move on to 13.2, kinetic theory of gases. So, why we need kinetic theory of gases? Okay, so class, the kinetic theory of gases will try to relate the macroscopic properties of gas. The macroscopic means something that we can measure. For example, the pressure, the temperature, the volume, the internal energy of the gases with the microscopic properties. Microscopic properties means something that we cannot see with our naked eye. Dengan mata kasar, you tak boleh nampak benda tu. For example, the motion of the atoms of molecule of the gases. So when we talk about the motion means we refer to the speed or the velocity of the gases. Betul kan? You tak akan boleh nampak molekul-molekul gas tengah bergerak dalam udara, betul? That's something that you tak boleh nak nampak dengan mata kasar. We just zoom in, that one we call microscopic. So in the kinetic theory of gases, we try to relate the macroscopic quantities like the pressure, the temperature with the microscopic quantity means the kinetic motion of the atoms, the movement of the gas molecule lah. So kita nak cuba relate kan, apa hubungan pressure, tekanan dengan kelajuan pergerakan gas, velocity of the gas? Apa kaitan temperature dengan kelajuan pergerakan gas molekul gas ni, the velocity of the gas? That one is what we are going to discuss under kinetic theory of gases lah. So, before we go further into the kinetic theory of gases, we have some assumption in this theory of gases. So, first, we assume all the gases are made up of identical atoms or molecule. Means that when you talk about the oxygen gas, so all the oxygen gas will have the same size of atoms or molecule, okay? Second one, all atoms or molecule are in constant, move randomly, and they will colliding each other and also with the wall of the container. Randomly here means that any molecule can move in any direction with any speed. Okay, you cannot control the movement of the atoms or molecule. They move randomly, secara rawak, in any directions. Okay, in any directions with any speed. And they will keep on collide each other and also with the wall of the container lah, where we put the gas. Number 3, all the collisions are considered as perfectly elastic collisions. So, okay, why? Because if in elastic, there will be a loss in kinetic energy. So, if we have loss in kinetic energy, nanti lama-lama atom dan molekul tu akan jadi makin perlahan dan akhirnya tidak bergerak. Tetapi sebenarnya dalam reality, benda ni tidak berlaku. So, all the atom and molecule is keep move randomly. So, it means that they are doing perfectly elastic collision. So, collision antara molekul ni mesti adalah perfectly elastic collision, so that their kinetic energy of the gases is always conserved. You can refer back to the concept about elastic collision in chapter 3. Okay. Number 4, the volume of the atom or molecule is negligible when compared with the volume occupied by the gas. So class, we understood that the size of the atoms and molecule is very small. So, we might ignore the volume of atom or molecule. So, when we talk about the volume of the gas, actually we consider the volume of the container. We consider the volume of the container that we store the gas, okay? So, if the container is 2 liter, means that the volume of the gas is 2 liter lah. So, the volume of the atoms and molecule is negligible. Number 5, Intermolecular forces are negligible except during the collisions. It means that there will be no interactions, attractions or repulsions between atom or molecule. So in between atoms and molecule gases, there will be no attraction force, there will be no repulsion force, but the force only acting on a molecule when they collide, when there is a collision in between the molecule or there is a collision with the wall of the container, and during that time only we have forces that we call impulsive force. Okay. The last one, the durations of collision is negligible compared with the time that spent traveling between collisions. So when we talk about the kinetic theory of gases, so we assume that the duration for the collisions we can be ignored because the time for the collisions is very short. Okay, very short. So compare with the time it traveled between collisions, so we can ignore the time taken for the collisions to occur. So this is the 6th assumption we have in kinetic theory of gases. So class, before we relate the pressure with the motion of the gas, so we are going to consider the velocity of the gas first. Okay, so how we are going to describe the velocity of a gas? So all gas are in random motion. So all molecule gas move in random motion. Each individual molecule, they move at different speed. Constantly they will collide each other and also with the wall of the container, and they will change direction. So the velocity of the molecule, gas molecule, can be positive and negative, depends on the direction of motion. Normally we assume the movement to the left and downward as negative, movement of gas to the upward and rightward is positive. So if we assume that all particles are moving equally in different directions, then we will find out that the average would give us 0. This value is very unhelpful when we talk about velocity. If we consider the velocity of the gas molecule, class, for example, this one, you see, each of these molecule of gases, they are moved randomly at different direction with different speed. Okay, so if we consider the velocity of the gas, I try to calculate the average velocity. Of all these gas molecules. So I put in the value of velocity for each of the gas. Then I divide by the numbers of molecule, 12. I have 12 molecule of gases. Surprisingly, I'll get the average value is 0. See, the value is 0, and this value is unhelpful. 0 doesn't tell us any information. So, in order to describe the motion of the gas, we cannot use the average velocity. We cannot calculate the average velocity, okay? Because the value will give us 0. So how we are going to describe the velocity of the gases? So class, to describe the velocity of gas molecule, first we will square all the molecular speed so that we will always get the positive velocity. So we will square the velocity of the gas, then we add up all this velocity squared. Okay, we add up all the velocity, then we divide by the numbers of molecule of the gas, then only we take the square root. So we will get what we call root mean square speed of gas molecule, denoted by V subscript RMS. vrms, root mean square speed of the gas. Okay, so this equation is quite long, so it can be simplified to this one lah. So we squared all the velocity, then we calculate the average value. We calculate the average value by divide with the numbers of molecule, then we square root. So class, remember for velocity of gas, to describe the velocity of gas, we didn't use the velocity, but then we use what we call root mean square speed of the gas. So, contohnya kita tengok balik gambar ni ya. Contohnya kita tengok balik gambar tadi, kan kita ada molekul-molekul gas dengan velocity yang berbeza-beza macam ni kan. Jadi, teacher can calculate the root mean square speed of the gas lah. Apa teacher buat? Teacher akan kuasa duakan setiap velocity molekul gas ni. I repeat, saya akan kuasa dua squarekan velocity of each of these molecule of gases. Then I divide by 12. Why I divide by 12? Sebab saya ada 12 biji molecule gas dekat sini. Then I take the square root. Then I'll get the root mean square speed of the gas is around 3.76 meter per second. Barulah nilai ni bermakna untuk kita sebab nilainya tak sama dengan kosong. Ingat in describe the velocity of the gas, we use root mean square speed. Okay, I repeat, to describe the velocity of the gas, we use root mean square speed. Alright, so of course lah, in this room there will be a lot more than 12 molecule of gases lah. Just teacher bagi example calculation lah, macam mana nak dapatkan root mean square speed gunakan 12 biji molekul ni lah. But then in a room we have thousands, millions of molecule of gases. Okay, so clear? This is what we call root mean square speed of gas.